Okay, I think we're recording. My name is Daniel Nelson. I'm a technical sales manager at RBR, based in the Seattle, Tacoma, Washington area. Today's presentation is about instruments that RBR supplies for use on the WireWalker platform. We're really excited to have today a double dose of WireWalker information for you, for the audience. We have today's presentation with our guest, Tamara Schlosser from SCRIPPS, discussing her research using data from the WireWalker. But then this evening, North America time, or tomorrow morning in Australia, you're able to join us for a presentation with Delmar Oceanographic and SCRIPPS, going into more detail about the profiling platform that is the WireWalker. So this is a repeat and a supplementary presentation, another chance to ask the experts about the WireWalker your questions with regards to how the technology works or how it might help your research. So again, we've got today's presentation, which is a bit more about data analysis and some of the results of the performance of the WireWalker. But then also you can go ask again and join us this evening for more information about the technology itself. So with that, I'm going to talk a little bit about RBR and what we do, what the instruments we supply for the WireWalker. As we've just mentioned before on other webinars, RBR manufactures a variety of instruments. We make sensors that do direct measurements and connect to your data collection platforms. We make autonomous loggers. CTDs is our core instrument, but then you can integrate a variety of other sensors into those instruments. Our loggers are autonomous instruments which utilize AA batteries. They have their own processors on the inside, a memory, and you're able to conduct your research using those instruments by themselves or in conjunction with other instruments. We make systems, which is basically our ability to help you get data from the bottom of the sea to the surface, and from the surface via telemetry to your servers through either inductive modem systems or telemetry systems that we have available. And finally, RBR repackages its sensor technology, its CTD technology, as well as integration of other sensors into different form factors that are able to be used for gliders or floats or other autonomous vehicles. So those are our OEM products. Here's a small snapshot of the core products that are available from RBR. We have our CTD systems in the middle with the RBR Concerto and the RBR Maestro. The RBR Maestro is our larger multi-parameter instrument that can integrate up to 10 channels. Over to the left, we have our dissolved oxygen sensor, which is an optical dissolved oxygen sensor. It measures not only oxygen saturation and concentration, but you get a temperature reading from it as well. We make compact sensors that, these are serial sensors that can be integrated into other platforms. On the right, we have our compact loggers, which are fully autonomous, either single or double channel instruments that you can either attach to additional moorings or actually conduct quite great science with them in their own right. So that's our Solo T temperature sensor there on the right. We make deep versions of our instruments that have titanium housings and some different sensor constructions, and many of them are rated up to 10,000 meters in depth. So our CTD is rated up to 6,000 meters, which you can see here, but then our other instruments can go deeper as well. And additionally, we make, this is an example of the RBR Legato CTD, which is part of our OEM line of instruments. This is a repackaged CTD that fits into the fairing or into the hull of gliders, such as the Sea Glider or Slocum gliders, and we supply those in conjunction with our OEM partners worldwide. So today, either in this presentation or later tonight, you're going to learn a lot about the WireWalker system. And simply put, the WireWalker is an autonomous profiling float. So it's a flotation system at the top. It's got a vehicle. It's not powered by anything. It's powered by the wave energy that it experiences. And using that wave energy, the frame ratchets itself down the cable, and then there's a click at the bottom and a release, and then it floats on its own buoyancy up to the surface, creating a very clean, quick profile that doesn't use any other electrical energy. It's purely a mechanical system. So this instrument was developed at SCRIPPS Institution of Oceanography. It's now been commercialized with Del Mar Oceanographic. Again, those folks are going to speak about that in detail tonight, which is really exciting. They do a great presentation about that. So I hope you join them for that. My talk today is just about RBR's instruments and what we supply for the WireWalker. As you can see in this photo over here, we've got an RBR CTD that's mounted inside the WireWalker. We also have an RBR Fermata battery canister. So I'm going to go into some of those details right now. The RBR Concerto and the RBR Maestro is really a great instrument to pair up with the WireWalker for a couple of reasons. First of all, it's a fast sampling CTD. You've got capabilities of 8 Hertz, 16 Hertz, or even 32 Hertz sampling with the CTDs. It's a very low powered instrument. So just as the WireWalker works without any electrical power itself, the CTDs from RBR are extremely low powered, which enables you to either sample faster, get more data, go for longer deployments, visit the system less to change out batteries. So really expanding opportunities for getting high resolution data, which we will learn more from Tamara in a few moments. Up on the screen, you can see our CTD. You can see its specs. It's calibrated to WOS accuracy standards. Some of the interesting features that enable great science using the WireWalker, in addition to the fast sampling, include directional dependent sampling. So basically, you set a threshold at a particular depth within the logger, and then once it reaches that, it switches to either an upcast or downcast sampling regime within the logger, and you're able to just sample fast on, for example, on the WireWalker, on the upcast only. So it senses when it's rising in the water, and it will do fast sampling then, and then it will do slow sampling on the way back down, and then that saves you battery power and memory to enable longer deployments. Standard RBR instruments are depth rated up to 750 meters. So you've got quite a wide range, but they can also go deeper with titanium housing. Other features include, you've got kind of some options with RBR. You can either just attach a Concerto as it is with its AA batteries and just run it autonomously for a certain length of time. You can connect it to an extra battery pack to make it go even longer, or additionally, you can connect it to a real-time telemetry system via an inductive modem to the RBR Cervelo, which is our marine telemetry unit, and then transmit your data in real time to a data hosting service from RBR, and then just sit back and receive your data as and when you want to. So additionally, RBR CTDs can act as sensor hubs, and you can integrate other sensors, analog and digital sensors, to the sensor hub and receive data directly through the RBR data stream. Here's kind of a simple set of pictures on how that works. So if you were to talk to RBR about instrumentation for the WireWalker, we would discuss obviously your application, we would discuss your technical specifications, your project specifications, and we would help you determine whether it would be suitable just to get the CTD as it comes, whether you would want to change the connector on the back end. So the red connector on the lower left is an example of our various connectors that you can add to an RBR Concerto or RBR Maestro. This particular one would connect to either a battery pack and then a patch cable that you can see on your screen. You could connect to the RBR Fermata battery canister, which holds 56 D-cell batteries and enables really a long time, up to nearly a year of deployment or longer with that. So basically unlimited power for your CTD and or other instruments as well. So that connection can go to the extra battery pack. And then You can also attach a subsurface modem that leads to a ferrite for an inductive modem system that then telemeters data up the jacketed cable to a modem and then further on to your servers via the rbr Cervelo. The rbr Cervelo is our marine telemetry unit, as I said. It includes a data controller, it includes memory, it includes 2 types of modems, including Iridium and GSM. Various options for getting your data include just going out to visit the buoy and putting in a USB stick into the rbr Cervelo and just downloading your data right there on site without having to pull everything up and to open up the logger. You could also connect to the logger via the patch cable that is supplied with the WireWalker system. Or you, if you have the Cervelo, you would get your data in real time via RBR's data hosting service. And an example of that is on the screen. So you could get data transmission every 30 minutes or every hour, just depending on your budget for Iridium service. We're going to learn today a lot from Tamara about some of the data she received from light sensors, fluorometers, optical backscatter sensors. So I'll let her do a lot of the detailed talking about that. But I just wanted to share today that it's not just CT and D that you can measure using the WireWalker, but you can attach a variety of instruments. Our colleagues at SCRIPPS and Del Mar will talk more about other types of things you can put on the payload for the WireWalker, including cameras, turbulence sensors, other types of optical sensors. But typically, when you integrate through an RBR CTD, you would include either a dissolved oxygen sensor, such as our optical sensor, the RBR CODA TODO. It has a fast response time of 1 second, and then cables into the CTD. So that's great for profiling. Also, you can have optical sensors such as the Wet Labs EcoPuck, transmissometers, turbidity sensors, fluorometers of different wavelengths, and light sensors. So these are some of the common sensors that are integrated, and we'll learn more about the results of that in a few moments from Tamara. The final thing I wanted to highlight was just that Tamara is a participant and a member of the RBR 2020 cohort. This was started at the very beginning of this year of 2020, where RBR selected a number of high-achieving young scientists or early career scientists, and Tamara is one of them. And as a benefit of that program, participants in the cohort are able to receive instruments from RBR to help further their research sort of on loan. They're able to receive mentoring. We've done science communications training throughout the year, engineering support. So we're really thrilled with the results and the work of these members of our cohort. And I think what you'll see today is you'll see some of that work represented in Tamara's presentation. So with that, I think I'm going to pass it to her. We're really glad to have Tamara with us. If you have any questions about RBR instrumentation as it relates to the WireWalker or anything else, you're welcome to contact me directly out west here in North America, or just our main number in Ottawa, Canada, which is you can see here on your screen. So thank you very much. With that, I will transfer the presentation to Tamara.
Great, thank you, Daniel. I'll just try sharing my screen. Hopefully this works. Okay, are you seeing it okay?
Yeah, it looks good. So just slideshow mode, please. There you go. Thanks very much. It's all you.
Thank you. Thank you, everyone, for joining. So I'll be presenting some analyses from some field data we collected last year in July from the Bay of Bengal, which is pictured here in the background. And so I'm looking at how monsoons and plumes limit chlorophyll fluorescence at the deep chlorophyll maximum. And I'm doing this work with my supervisor, Andrew Lucas, at SCRIPPS, as well as Thomas Farrar from Woods Hole. So firstly, I wanted to talk about why I care about primary productivity. And I care about primary productivity because it has implications for example, the biological pump of carbon, which I'm showing here on the right. So the biological pump of carbon describes how carbon dioxide from the atmosphere may get transported to the deep ocean. And a large part of this pump is the carbon fixation by phytoplankton. So that's one reason why we care about the primary productivity in our oceans. Another reason is phytoplankton impact the upper ocean heat content. So when chlorophyll concentrations are larger, light can't penetrate as deeply as it could if chlorophyll concentrations were smaller. And so when we have these large concentrations of chlorophyll, we may actually be increasing the amount of heat that is trapped in the upper layers of the ocean. And so that's another reason why we might care about primary productivity. So this primary productivity can be limited by nutrients or light, typically. And so changing now to the monsoon in the region. So the southwest monsoon affects the Indian subcontinent, and it's economically important, but also leads to devastating floods annually. And predicting the monsoon is especially difficult and of utmost importance. And this is the focus of the ongoing research like MESOBOB and the previous SERI research in the area, as well as numerous other research bodies, but I am part of the MESOBOB research project. And so under light limited conditions, primary productivity can depend on cloudiness, which is a characteristic of the monsoon, as well as the optical qualities of water. So one optical quality would be this self-shading, where phytoplankton concentrations influence the penetration of light. So that's one way in which, the optical qualities of water can be modified. Losing my voice. So in July 2019, we conducted a field experiment in the Bay of Bengal for 18 days. Sorry, I'm just having a lozenge. Hopefully that'll fix my voice. Okay, sorry. So I'm showing the Bay of Bengal here in the upper left panel. And in the bottom panel, I'm just zooming in on this red square region. And so this is where specifically we deployed 3 Wirewalker profilers. So they all drifted to the southeast. They were not anchored. And there is a eddy that was present, which you can see in the black contours. But just generally in the bay, showing the shortwave radiation for the month of July, that's coloured with the grayscale here. So you can see towards the northern and eastern sections of the bay, there was less light available. So there is some spatial dependency on light availability in the bay. And before I show more observations, I should just show you the design of the drifters. So we have a Hui mid-ocean buoy at the surface, where I'm only showing shortwave radiation, but there's numerous other products. Just in general, I'm only going to be talking here about what I'm actually showing today. Then the Wirewalker profiler was profiling over the upper 100 meters of the water column. In addition to the CTD, at the chlorophyll A fluorescence is a proxy for the chlorophyll concentration. And I should add that we did not calibrate these in the field, so concentrations presented here are not precise. We observed irradiance at 4 wavelengths from 380 to 530 nanometers. So this is not the full range of photosynthetically available radiation, or PAR, which is from 400 to 700. And so what I've done here is I've extrapolated our observed range and just assumed that it's representative of the full PAR range. We additionally observed acoustic backscatter from Nortec signature, which was mounted on the Wirewalker. And I believe everything else Daniel has already mentioned, so we'll just move forward. So just in case you don't know much about the Bay of Bengal, I wanted to just present to you some typical values for shortwave radiation varying by month on the x-axis. And so this is the drop flux product averaged over 10 years. In the middle panel showing the Modus Aqua surface chlorophyll A. So this is a satellite observation. And then lastly here, the Modus Aqua light attenuation at 490 nanometers. And just note that I have reversed the y-axis here just so it looks more like the chlorophyll A. And I've highlighted the southwest monsoon in grey, just so this is the time period we're interested in, where the black box plots show our observations, just so you can contrast. And so I mainly wanted to point out that in addition to there being spatial variability in shortwave radiation in July, there's also spatial variability in the seasonal trends. The colours here refer to the colour of the cross. So this dark purple colour has the largest variability in a minimum during southwest monsoon and a maximum in about April. And if we contrast that to the most equatorward point in dark red, you can see by contrast, this one is much flatter. So there is there's larger seasonal variations in shortwave radiation as you go towards the north and towards the east of the bay. Interestingly, there's actually larger surface chlorophyll A typically during the monsoon months. So not when there's the most shortwave radiation available. And as I mentioned earlier, chlorophyll A concentrations do influence the penetration of light. And so that is why this K490 plot looks so similar to chlorophyll A. And so you can see that during the southwest monsoon, there's a lot of variability across the bay in how far light is penetrating. And there's some variability in exactly which month light is reducing in its penetration. So instead of penetrating to say 30 meters, it's only penetrating to more like 20 meters, for example. And I'm contrasting here to our observations and to values from a number of field experiments or field campaigns, sorry, from this paper. And so you can see that there is potentially this product is a overestimate. Sorry. So looking more at our observations now that you have a general idea of the bay, showing in the top panel here is PAR or photosynthetically available radiation. So you can see that there was some temporal variability, particularly towards the end of the field experiment. Next showing here, chlorophyll A concentrations. And I've also contoured the isopycnal depths for two different isopycnals, where this blue one is a 1021.5. And you can see this quite nicely intersects the depths where chlorophyll A was largest. Next, I'm showing the optical backscatter here. So OBS is optical backscatter. And you can see before July 15, we observed some really large values. So there was actually a coastal plume or filament. Waters with probably high sediment concentrations were being evicted from coastal waters offshore. And this was even quite obvious just from the ship. But after July 15, the drifters have moved out of this coastal plume and the values are overall much smaller. But you can kind of see around when chlorophyll A values were large, there was subsignal near this isopycnal, but I'll go into the detail more later. And lastly, in these two panels showing the acoustic backscatter, so that's ABS here. Just showing that during the day, there's vertical migration occurring at 300 meters as well as more like 100 meters. And this is detectable at both frequencies, this vertical migration. And then during the day, during the nighttime, the values are largest at the deep chlorophyll maximum. So there's a vertical migration to depth during the day and then back to the surface at night. And this is likely composed of things like zooplankton and fish, some of which may be feeding on the deep chlorophyll maximum. Because we had such high vertical resolution observations, what we're able to do is transform our observations from depth coordinates to along isopycnal coordinates. And then to avoid stretching, I convert back to the depth coordinates using the average depth of each isopycnal. So kind of like a pseudo depth. And the benefit of this, it just makes it a lot easier to see that chlorophyll A and optical backscatter was large along a constant isopycnal. And it's easier to also look at how this is changing over time. And it may be also easier to read the acoustic backscatter in this figure. So really just showing that during the day we have vertical migration to depth, and then at night it's coming up to the surface, and it's similar for both of these quantities. So next I wanted to talk more about light, our observations of light. So we observed raw irradiance that I then fit to an exponential curve to get this K value, this light attenuation. And so I fit for every wavelength that we observed. So ranging from 380 to 532. And showing the results here on the left. And I've indicated July 15 again, just so you can see when the drifters might have been inside the coastal plume and when they were leaving or out of the coastal plume. And you can see that when the profilers were within the coastal plume, it varies depending on the wavelength. But for example, at this 490 nanometers, the e-folding scale of light was much smaller than if you compare to, say, at the end of the field experiment. And even once the drifters were outside of this coastal plume, there was some temporal variability. So our light attenuation values were definitely not constant in time. So one question we had was, what impact is this having on subsurface irradiance? So to test this, I'm looking at 3 different test cases. The first, instead of using our observed shortwave radiation, I use some clear skies estimate where it's the same amount of light available every day. So that's the orange case. Next, instead of using the time variable light attenuation, I use just a constant value, which is the blue case. And I chose the minimum just to try and consider, like, what if this coastal plume wasn't present and chlorophyll A concentrations weren't causing light attenuation to decrease. And lastly, instead of looking at the amount of irradiance that was available along isopycnal that we observed, which is shown in black here, I've low pass filtered this depth to remove the influence of internal waves. So the purple case is asking how much of an impact did internal waves have on subsurface irradiance at the deep chlorophyll maximum. So here I'm showing the along-isopycnal change in PAR as a percent. You can see at the start of the period, the largest impact was due to water clarity. So this is when the drifter was in that coastal plume. But once the drifters are outside of the coastal plume, we start having some more shaded days. And so the impact of cloud cover is having a much larger influence. So overall, cloud cover had the largest impact on subsurface irradiance at the deep chlorophyll maxima, where chlorophyll A was largest. But the impact due to water clarity was still significant. And although internal waves had a relatively small influence compared to the other two, it still gets up to about 45%. So it's not an insignificant influence, just not as impactful as the other two signals. So bringing it all together, I want to statistically check that productivity was actually light limited in the Bay. And although I say productivity, I do mean chlorophyll A concentrations, of course, because I didn't actually observe primary productivity. So just forgive me if I'm saying productivity in the presentation. So what I've done here is I've done a lagged cross-correlation analysis to contrast PAR and chlorophyll A. And what I've done is I've removed the daily average chlorophyll A value. So I'm only comparing the diel variability or the diurnal variability. And if I have a lag between the black and the green lines of 1.6 hours, I get a significant correlation of 0.69. So I've already lagged the two signals in this plot, so that's why they line up so well. And you can see that, for example, on July 21, we have some of the largest variations in the chlorophyll A over a day. And it was also a very sunny day. And if we contrast this, to example, to July 17, it's a much more shaded day, and there was much smaller changes in chlorophyll A. And so to take it a step further, in these bottom panels, I'm contrasting on the x-axis PAR here and shortwave radiation below in this row. And then on the x-axis, I'm comparing it to the diel range in chlorophyll A. So this is like what I'm showing in this panel A. And then in the right column, I'm showing, comparing it to the average chlorophyll A in the day. So the mean value on that day. And you can see for all of these quantities, there is a linear relationship indicating that chlorophyll A concentrations were limited by light. So when there was more light available in a day, either due to shortwave radiation or PAR, which additionally includes the influence of the water's optical qualities, there was higher chlorophyll A concentrations, both the average in the day as well as this diurnal or diel variability. And how good this fit is, I found to be, or the performance rather, to be quite surprising, given that I'm not considering anything like nutrient limitations or grazing. You know, if you look at the end of this record, there's not as coherent a relationship. So I'll talk about that a bit more on the next slide. So really this fit is really quite surprising, but does indicate that there was a strong correlation between these two signals. And so during this time period, at least, it looks like chlorophyll A concentrations were limited by light. And so lastly, what I wanted to do is focus a little bit more on this diel variability. So firstly here, I'm showing chlorophyll A in green, the diel variability only, and then optical backscatter on the right here in brown. Just wanted to show how nicely these two correlate. So this gives us some confidence that what we're observing is actually a change in biomass, and not, for example, a change in the photosynthetic capacity of in phytoplankton. So this is what occurs during when circadian rhythms are occurring, for example. But because we're actually able to pick up a response in the optical backscatter, we have some confidence that there's a change in biomass that is occurring. And this is significant when we consider the acoustic backscatter, which shows this vertical migration occurring to the surface at night and to depth during the day. So this was phase locked to the shortwave radiation, but with a 12-hour lag. And so altogether, these results are consistent with nighttime grazing being responsible for the diel variability in chlorophyll A. And so finally, to conclude, our chlorophyll A concentrations over the course of the day were tightly connected to and well predicted by our optical observations of subsurface irradiance. Subsurface irradiance was dependent on cloudiness, which is a characteristic of the monsoon, as well as the water clarity, which was reduced within a coastal filament. Our observations indicate that monsoonal weather patterns likely impact subsurface primary productivity in the Bay of Bengal. And this would be especially in the northern and eastern sections of the Bay, where shortwave radiation is typically smaller and there's larger seasonal variability in these quantities. And lastly, chlorophyll A, optical backscatter and acoustic backscatter were tightly coupled at the deep chlorophyll maximum. So vertically migrating organisms can transport carbon across the picnic line, indicating that monsoons and plumes may modify the transfer of carbon from the atmosphere to the deep ocean by limiting chlorophyll A and phytoplankton biomass. But this is something that requires further research, but is a very interesting result of our research. So thank you very much for staying with me, and thank you to the crew and all the science personnel who assisted with the fieldwork. Thank you.
Thanks, Tamara. That was awesome. I really appreciate that. I'd like to open up we've got a nice audience today, about 15 people joining us. So if anybody has any questions for Tamara, that would be excellent. Please feel free to enter them in the chat window or to just open your mic and ask. Okay. I think maybe I'll kick it off with a sort of some less technical questions, but still of interest to myself and maybe others. In terms of the just basic question, in terms of the monsoon season, Tamara, is that like a fixed defined period, or what are the criteria that defines the beginning and the end of this monsoon period that you were discussing?
No, it's not fixed. So if I go back, oh, if it'll let me. So the monsoon was actually delayed. It's becoming active really during this end period. So I haven't shown wind stress observations, but the wind stress was largely increasing over this period. But this break period is what we call it, is what occurred earlier on. And so that's why we observed sunnier days. And so to some degree in this field experiment, we kind of missed the really active period of the monsoon, unfortunately. Although not for me, I was very happy with my observations. And I think the reason why last year it was delayed was because there was a tropical cyclone that was present earlier in the year. And so that impacts the start of the monsoon. But definitely trying to predict the start of the monsoon is really important for the region. And so that's trying to improve our predictions is one of the goals of the MUSABOR project.
Gotcha. I don't want to take over the whole talk. Does anybody have any questions for Tamara? In terms of, I guess I got another one. In terms of the reviewing the data, I mean, it's a massive data file that comes from the profiler and from the instruments. What were some of the challenges, and I guess how did that came with trying to evaluate such a large data set, high resolution data set?
Well, I guess something that we almost always do with the Wirewalker data is because it's originally at 6 hertz, I believe. Well, I think it was 6 hertz for this experiment, and so very high resolution with and the ascent rate of the Wirewalker, I think, was about 30 centimeters per second for this project. So the first step, what we do is we grid it. And so to do that, we average any, if we have multiple points within a 25 centimeter bin, then we average those points to get one value. And so we lower the vertical resolution to 25 centimeters, but that at least gives us a consistent picture because, sometimes we have more points at certain depth ranges than others. So that's just the first step we always do. And that makes the data much more manageable to start with. In particular, working with the irradiance data was quite challenging because it is a vertical profiler. So to measure downward irradiance, you obviously need an upward looking sensor. And if the Wirewalker is moving at all, you may have larger or smaller irradiance observations. But what I realized the more I worked with this irradiance data and learnt about it, because I'm not I haven't previously worked with optical data like this, is that there's a lot of natural variations in irradiance over depth. So it is common for there to be regions where there's more or less light available due to processes like refraction. And so I guess I realized that a lot of what the stuff I was observing that I thought was the Wirewalker was actually just real. After talking to some more specialists. And so I found that really interesting. And so I'm using a depth constant value for light attenuation here, but as I continue working on this, I may actually use depth variable light attenuation because we're able to actually observe these high resolution variations in irradiance, which, typically it's very difficult to get these observations.
Gotcha. We have a question. Thank you for that. We have a question from Richard Davis. I don't know if you can see it in the chat window, but it says, did you correct your estimated chlorophyll concentrations for photochemical quenching of fluorescence by high irradiance?
Yes. So thank you for asking. I forgot to mention that. Yes. So I did. We did correct our observations, but I believe it was really only the upper 20 meters where we had any correction, and the corrections were, I think, very small. I think less than 10% of the average. So that the amount of quenching that was occurring was relatively small. And that is probably in large part due to the depth of the deep chlorophyll maximum. It's about 40 meters at this site. So it seems like where chlorophyll values were largest, there wasn't much quenching going on. But definitely at the surface, on some days there was quenching occurring. And so I believe I did a correlation analysis between our irradiance and the chlorophyll A in order to eliminate that.
Thank you for that. Any other questions from the crowd? All right, well, I'll just have one more final one. What's next for you, Tamara, and for this particular research direction?
Yep, so for this work, I've been focusing on how the biology were impacted by varying light attenuation. And obviously the biology also influences light attenuation. But in future, I want to look more at how these changes in light attenuation have impacted the heat budget. So I talked about upper ocean heat content before as a motivation. And so I would like to, as a next step, look more in that direction. We additionally had microstructure instruments mounted on the Wirewalker. So I may be able to do quite a good job at calculating the heat budget. And so that would be the next step. So related, but just looking more at the heat instead of the chlorophyll A concentrations.
Excellent. Well, Tamara, thank you so much for joining RBR today. I think we had a nice audience with us, and hopefully they took value from the presentations today. Again, I want to remind everyone that there is an evening presentation, North America time, morning in Australia, with regards to more details about the technology behind and the science behind the Wirewalker profiler. So please join us for that. That's hosted by my colleague Steph Stimson in Australia. And otherwise, we thank everyone for their participation and for joining us. And Tamara, thank you again for joining us today.
Great, thank you.
Take care. We'll see you again.